Hi, good morning, everyone. Thank you for joining us. I'm Heidi Zimmerman, Executive Director at AWT, and I have just a few housekeeping notes. When you signed in, you'll notice that you were in listen-only mode, but we do encourage questions. So if you have any questions as we're going through, just type those in the chat box and we'll take those at the end. Also, this webinar is being recorded and it will be on the AWT members only website later this week, and you will also get a PDF copy of the slides later today as well. So with that, let me introduce our speaker today. Jim Collins is the Business Development Manager for Brenntag Mid-South. Jim is a water treatment professional with 38 years of experience dealing with industrial water and wastewater. He is currently president of the Indiana Industrial Operators Association, is a registered industrial wastewater professional in Indiana, a certified electro-finisher, and on the board of directors of the Indianapolis branch of the National Association of Surface Finishers. Jim has a bachelor's degree in marketing from Indiana State University, and Jim will be at the Brenntag booth at the AWT convention and will also be presenting additional information at the Brenntag's Metal Removal Commercial Corner at AWT's convention in Grand Rapids, Michigan on Thursday, September 14th at 8 a.m. So with that, let me turn the program over to Jim.
Hello, everyone. It's very nice to be here today, and this is a very timely subject. It's chelated metals, and I'll tell you why. In the United States, the metal finishing industry is alive and well. I want to say metal finishing industry, and I want to say surface finishing industry. And what we have going on is more new business coming into this country. And we have the automotive industry, the aerospace industry, and everyone else involved, especially in housing as well, at creating new finishes that are more environmental friendly, certainly more user friendly. And that's the automotive industry. They're creating finishes that are lightweight. We're going more and more to plating on plastics for a lot of the components of the car. We're going a lot more to this as well in household faucets, if you will, where we're trying to get away from lead and copper and still get the performance we need in the household. We're going more to plating on plastics there. In metal finishing, and surface finishing as well, the goal of the bath, the plating bath that is to keep the metals soluble as long as possible at all cost. While this is good to our people in the plating line, out on the finishing line, it's very detrimental to the guy in the wastewater treatment line. And we're going to talk about today from a wastewater treatment standpoint, what we have to do in order to reverse engineer what they are doing out on the plating line. So I'm going to start advancing some of these slides here. Today, I want to talk about what chelators do, where chelators are used. I want to talk about breaking chelated metals. We're going to talk about alternatives to chelants out here in the field from a chemical standpoint. I also want to troubleshoot clarifiers. I've really ran into that a lot lately. And if you're having issues with the clarifier, many times the end result will be something very similar to what you see when you have chelated metals. And I definitely want to talk about jar testing here too. So that's what we're going to try to get done here in the next several minutes. And I hope you have some good questions for that. We'll be very happy to answer them. When you are a chemist, when you're a formulating chemist at a proprietary supplier of a cleaner, of a plating process, you realize you've got to have a chelate present in your compounds. A good definition for that chemist is a heterocyclic ring containing two metal ions attached by coordinate bonds to at least two nonmetal ions in the same molecule. That's how the chemist looks at this. And again, the chemist is looking for the ability to create and maintain soluble metals within that plating bath at all costs. That's the number one function for him. A chelate for the wastewater operator is organic compounds having the ability to withdraw ions from their water solutions into soluble complexes. Later in this webinar, we're going to talk about more common relevant chelants, but the number one chelant of concern, as I've tabulated in my years of work here, is ethylene diamine tetraacetic acid, EDTA. EDTA has an extremely strong affinity for calcium, for manganese, for iron, for the elements of water that we'll talk about here in a few minutes. EDTA also has an extremely high affinity for zinc, copper, nickel, chrome, cad, all of the metals that are on our permit that we've got to remove. It will, for lack of a better term, attempt to complex them as well as it will the calcium and all the other components in the water stream that we're facing. A complexer. There's chelants, sequestrants, and a complexer. Some of these products are classified as complexers in the bath. Complexer can be defined as an organic or inorganic compound having the ability to combine with metal ions and hold them into solution. And this particular definition here has, there's not a better definition of that than sodium cyanide. And for years and years, cyanide has been present in these plating baths. Zinc cyanide is a classic example. Cyanide copper is another. You really would never run into a cyanide nickel process. You really would run into a cyanide chromium treatment plating process. But where you've got a lot of zinc, where you've got a lot of copper, where you've got, well, in some cases, maybe some cadmium here, you will have the presence of cyanide. Silver is another. Silver cyanide for conductors out here, connections and conductors of electricity, that's very, very present. And those baths can typically be very difficult to break. But sodium cyanide is a classic example of a complexer that's in a bath that we must treat in our wastewater treatment process. The sodium cyanide, obviously we know that it's toxic. We also know that it's going to hold the metals in solution. So there's a double-edged sword to these cyanide plating baths. Why are chelators needed? Chelators tie up elements in water. As we know with water, one of two things is going to happen. That drop of water on a substrate is either going to form a barrier or it's going to corrode. And when it wants to form a barrier, in many cases this is an alkaline barrier, what is happening is the iron, especially calcium, in some ways manganese, are going to start to form a barrier film on the substrate. Well, if we start to form that barrier substrate, the part is going to be very difficult to plate. It's going to be very difficult to clean. And as a result, our goal with our chelators, we want to keep this barrier from forming. We want to keep the elements soluble longer, keep them in solution longer. Thus, the reason why chelators are needed. And a real good chelator, if you would, for something like this is sodium gluconate. I even like sodium glucoheptanate and gluconic acid. They're excellent sequestrants of the water, of the hardness that can be in the water. The problem is, just like with EDTA, they will have a tendency to also want to complex our metals. And once again, when they complex the requer metals, we're going to be in trouble in our ability to drop them out as they're insoluble hydroxides. In cleaning process, when we use a chelator, we've got to prevent deposition on the work surface. In a second here, we're going to break down a cleaner. We're going to break down a cleaner that's out on the line, and I'll tell you how this will indeed occur. The next slide here is actually it. We're talking about metal cleaners and their compounds. We're gonna go through the components in this compound and how they all interact. When I talk about base here, I'm talking about in particular an alkaline cleaner where we need to have the art of saponification occur, where we've got to clean oils and greases and cutting fluids and all of that off of our base metal prior to preparation. The base in this case is either a sodium hydroxide or certainly a potassium hydroxide. Potassium hydroxide gives us a little more soluble alkalinity, if you would, but caustic soda is the #1 base that's used in this process. The next thing that's very important in this cleaner are the surfactants. Surfactants and chelants and sequestrant packages really work hand in hand. You cannot have a successful metal cleaner without the proper surfactant package and without the proper sequestration package. The surfactant in this case is there to reduce the surface tension of the solution. It's there to emulsify free oils, and it's there for any other wetting that we need, where we wet the base metal, allowing for saponification to occur. Now, the sequestration package, or the chelants, also can be called the chelants, are necessary because if the water quality is hard in this particular cleaning bath, the surfactants struggle to wet, to emulsify, and to assist in saponification. So if we have the proper sequestration product or chelant present in this formulation, it will definitely make the surfactant that much more effective, and that's what the end customer needs. If you look at my fourth point here, secondary alkali builders, we've got to maximize alkalinity because, again, the #1 function when you're cleaning metals is saponification. The more you have total alkalinity and reserve alkalinity, the more success you're going to have in the cleaning process. The fifth item on here is the coupling package. A classic example of that is sodium xylene sulfonate or phosphate esters that you need in order to assure yourself that all gallons of this cleaning solution are homogeneous. They're all one. We had no stratification in the drum, and gallon 1 out of that drum is going to be as good as gallon 55. All of these components here work together to create a compound. Sequestration packages or chelants can be as high as 20% by volume. I've seen them that high. When you run a cleaner with that high a chelant in it, you've really got to have a real good reason for that. And if your application, you being the customer, if your application is not needing this much sequestrant, you've got to get with your chemical supplier and say, hey, reformulate me a cleaner that I can live with, not only on the line, but certainly in waste treatment. I'm going to talk about the solubility curve here. I've got a picture on the next slide and a nice little illustration about how you can struggle despite the solubility curve. On the next slide here, x-axis is horizontal, has a pH scale of 0 to 12. The y-axis will be vertical, and it's your metal concentrations in ppm. We all know that when you run into a plating and surface finishing facilities, especially job shops, they are multi-metal job shops. They are doing copper, nickel, chrome. Some of them could be doing, every finish that there is out here. They could be doing cleaning. They can be doing deburring. Well, what happens is they've got many different metals that they've got to remove. And as you can see from heavy metal precipitation here, if you take a look at this chart, if you look at this solubility curve, you would think that this is going to be very, very easy. All I've got to do, for example, if I'm dropping copper out of solution, which is Cu, is have that pH at 8, and all of my copper is going to drop out. If I'm going to be dropping out nickel, I need to be at 10.5, and it should be no problem whatsoever. Well, we're going to talk about this here shortly. I want to show you something very interesting. Look how zinc and chrome will start to come back out of solution. See, as we're down, for example, with Cr+3, which is trivalent chrome, as we are down at a pH of 7, we are maximizing the complexation of trivalent chromium hydroxide. If our pH gets too high, if we've got to drop nickel out, look what happens if I've got chrome present in that solution. My chrome is going to start going out of solution. Chrome and zinc are amphoteric, meaning they will go out of solution. However, if the pH gets too high, they will start to go back out of solution, solubilize, and then your wastewater treatment process is going to be in trouble. Keep in mind that this chart right here is written, this is the hydroxide solubility chart. It's a US EPA generated solubility chart or solubility curve. The next slide, guess what? Look what happens. We're throwing that chart out the window. If chelation occurs, that chart is completely irrelevant. You can have, if you've got chelated zinc, you can have that pH sitting exactly to the T where it needs to be when you are taking zinc out as a hydroxide. But because it has chelated, it's not going to come out of solution. It's already locked up and we're in trouble. So let's talk about this further. I'm a pollution prevention kind of guy. I'm a P2 guy. I want to walk up on the line. I want to see what we're doing up on the line. I want to take a look at the concentrations we're running on the line and see what we can do to make things better. So how do we prevent chelation? How do we prevent sequestration? And I want to talk to you further about the treatment of chelated waste streams from a batch treatment standpoint and from a continuous flow-through process here. I like to go up on the line, and I like to utilize, for the most part, the fundamentals of cleaning in order to achieve my goals of cleaning. I want to analyze the time, the temperature, the agitation, and the concentration that I am seeing going on up on the line. My goal is to run the lowest level of cleaning concentration possible by working with the other fundamentals of the cleaning process. If I can raise my temperature, the more my temperature is up, the less likely I'm going to need the detergents to perform their function. If I've got good time, if I've got good agitation, it can allow me to run less concentration of the cleaner. Therefore, the likelihood of less concentration of chelants in the influent to waste treatment, it appears that that will happen, and I've seen it happen firsthand there. I like to monitor the cleaning concentration. I like to also make sure that I've got drip shields wherever possible to keep as much cleaner in the tank and not allowing the cleaner to be drug into rinse waters. The problem you have in a finishing shop, the problem begins when we go out of the work tank, be it the cleaning tank, be it the etching tank, be it the plating tank. When we come out of that tank and when we go into the rinse waters, that's where wastewater treatment begins. Up on the line, if we control the chelants and the cleaners and all of that, the better chances we're going to have success. I like to reformulate cleaners wherever possible. If I've got to give you a classic example. I had a customer the other day that they were on city water on their cleaning process. The city water had a lot of minerals in it. It still met the drinking water standard, but it had minerals in it. This particular company went to RO water. They put RO in. All of a sudden had trouble in wastewater treatment. Chelated metals. Why? Because the free chelant in that water was now very prevalent because the chelants that we had that were tying up the minerals in the city water were no longer needed in RO. So they went and complexed our zinc and our copper, and it took us a little bit of time to figure that out. So what did we do? We got with the people that make the cleaner, and they decreased the amount of chelants, and guess what? We're cleaning better than ever, and wastewater treatment can't be going better. So reformulation can happen. I've got some other pre-treatment options here. In wastewater treatment, my goal with a coagulant is to tie up the chelant, thus allowing the metal to be more free to precipitate as a hydroxide. If I have a product that's prone to chelation, in particular a coagulant, and especially calcium and magnesium, if I can add those products, those chemistries at a pH below 3, and as my pH comes up, I chelate my calcium, leaving the metal more free to precipitate the hydroxide. EDTA loves calcium. If I have EDTA in that bath, and I know that it's going to be free, I am definitely adding some calcium chloride at a pH of 3 or below, because as I break my pH up in order to precipitate out my metals, I'm going to form a complex between the chelant and the calcium, which is exactly what I want. I want a complex between calcium and chelant. I do not want a complex between zinc or copper and chelant. So I like to add my coagulants, if you would, at a low pH, and I've had great success doing this, by the way. I want chelated coagulant, not chelated metals. And magnesium chloride will work as well. We all know what magnesium sulfate is. Magnesium sulfate is Epsom salts. Let's say we've already complexed. We need to talk about this. I want to add something back briefly. When your pH is below 3, you have truly no chelation. The only chelation that will occur at a pH below 3 is going to happen with citric acid. And you typically don't have citric acid as a chelant in an alkaline bath. You can run into that where you're doing some descaling. So I wanted to make that clear before we go further. Once my metal has complexed, here I'm talking about breaking of chelated metals, the complex must be broken. And in today's world, we are seeing a record amount of zinc nickel alloy plating being done out here. In the old days, brakes would last 20,000 miles, and you had to go get the brakes redone. The new zinc nickel alloy plating process is guaranteed, these brake components now, they're being guaranteed to 100,000 miles, which is absolutely incredible. And it's actually working out to be that way. Our salt spray tests are showing that. Zinc nickel alloy has a very unique coolant in it. Think about what I'm saying when I'm saying zinc nickel alloy. I am hydrotroping, for lack of a better term, two metals together to form one soluble complex for electrodeposition onto the substrate. I've got to keep zinc in solution. I've got to keep nickel in solution in order to maximize my deposition. And my coolant of choice in this case, in many cases, is an amine. Is a triethanolamine, a monoethanolamine, a diethanolamine, or a combination of the above. The way to truly get rid of them at the very beginning of this process is I will flow my rinse waters into my batch tank, and I will set my millivolt reading at plus 500 MV, set my pH at 7. I will introduce bleach, and I will burn up the amines. That's vintage oxidation. Now, there's certainly other chelated baths. When you are running into a situation where you're doing electroless nickel plating, oxidation is more effective there with potassium permanganate. I have better luck of burning up the coolant package in electroless nickel with potassium permanganate. Bleach is not as effective there. In zinc nickel alloy plating influence to the system, I'm having much better luck with bleach. Sulfide treatments are so important, and we have done a lot of research to come up with the right sulfide complexes in order to precipitate these metals out. Remember earlier, you saw the solubility curve of metal hydroxide precipitation. A sulfide treatment solubility curve does not exist. It's a linear line. And what I mean by that is once you get, from a stoichiometric standpoint, the proper amount of sulfide in the stream, you will find all metal will start to drop out regardless of pH. One word of caution, you really don't ever want to add a sulfide at any pH below 7. I know there are those that say you can add it at 6 and 5. I'm not going to do it because you run the risk of potential toxicity if you run it below that pH. I like to take my pH to anywhere from 7 to 9 where I'm heavily chelated. Then I do the sulfide treatment, and I've had real good luck with that, and it continues to be a mainstream in my process all the time. pH adjustment. Earlier, I talked about I want to adjust my pH low. At that low pH, at below 3 again, you're going to have soluble metal, certainly. You're certainly going to have chelants that are not interested in complexing a valence. That's when you add your product. That's when you add your coagulant, if you will. And you definitely want your coagulant to be one that the chelants have a high affinity for. And again, we talked about calcium, or pretty much all of them have a high affinity for calcium. In chelation, there's a stability constant ratio. That tells you what product will complex quite readily another chelant. That's very important for you to understand, especially those of you that formulate cleaners. You need to know, you need to really be versed in the stability constant ratio of chemistries when you're creating a bath and when you're creating a cleaner. Ion exchange methods. You know, in today's world, these ion exchange processes, they're getting better and better. There's a lot of R&D. There's a lot of resin specific of metal specific resins. There's a lot of those out here today as well. And I like them. I'm having good success with them as well. Now, when I talk about plate out, I like hydrometallurgy. That's what I mean by here. When I've got chelated copper, you know what I do? I will go and I will get steel wool or powdered steel, and I will put it over in a tank, in a vessel, and I will introduce 1 amp of current to that bath. And even though the copper solution is not good enough for the plating bath, it's still going to be very high in concentration for waste treatment. I will simply plate that copper onto steel wool and onto powdered steel and sell that copper to a copper scrap dealer. It's worth a lot of money, and lately copper prices have really taken off again. That's called a plate out. You can also do that with nickel as well. So, and what that will do, you can get, let's say you're going in that bath and you're at 100 ppm copper. You can plate that out to where the soluble copper residual is 5 ppm or less. And we do that with success. Now, you really see this happening at plating on plastics industry, where copper is so critical, where copper is the first step in the electrodeposition process. You're going to run into a lot of chelated copper there. I like to know, are my metals total or dissolved? Dissolved, if they're dissolved, if they're not removed by filtration, you're going to have turbid or colored water. If it is total, you've got suspended solids. We're going to talk about this on the next slide as well. Dissolved metal typically tells you chelation could have occurred. Suspended solids, you might not have chelated, you might not have chelation, but you better start addressing your coagulation process or you're not going to make it. Here's what I like to do. I like to filter. If I'm having trouble in waste treatment, I'll filter the sample. If that filtered is good, we've got suspended solids. We are not having the good performance from our anionic flocculant. We've really got to address that. Or we're having equipment problems. Is a polishing filter not working right? Is the clarifier overloaded? We'll touch on that briefly here in a moment. If the filtered sample is bad, if you filter that sample and it still comes back bad after you've checked it on the Hawk test kit or the atomic absorption unit, if the metals are dissolved and the filtered is bad, you probably chelated. I like to add a drop of sodium dimethyl dithiocarbamate to 10 mils of this particular solution to see if there's a yellow precipitate present. If that indeed occurs and you start to see pin flock, that tells you that chelation in all likelihood has occurred. In jar testing, there's a lot of new coagulants out here. Your coagulant, again, has got to be specific. It's got to have an affinity for chelants. We formulate many new coagulants with this in mind. Do we have to increase the dose rate? Do we have to raise or lower the pH in order to introduce the coagulant? Are we using sulfide precipitators and at what concentration? All of these can happen in jar testing. Alternative chemistries out here are chelate-free cleaners. They will work. They will work in many applications, but they certainly are not going to work in all applications. We need to really, really keep that in mind. I just want to give you a good definition of coagulation. It's short and simple. I define it as the neutralization of anions present in an influent. You must neutralize anions. You must get the net positive in order that you be successful in creating insoluble metal hydroxides or insoluble metal sulfides. The coagulant is cationic in charge, and that's its function. Let's talk briefly about this right here, because so many times I've had customers have trouble with clarifiers. They think, well, my numbers are high, I must be chelated. We've got a lot of industry out here expanding, and the last place it gets expanded is wastewater treatment. Many times they run into a situation where the clarifier is just simply not big enough. And what I want you to do in that clarifier, check your coagulation. Check your flocculation. Get out the jar. Don't be afraid to jar test. Are your suspended solids too low? You know, there's such a thing as water being too clean. And if that water is too clean, it's very difficult to treat, as we know. Has there been a change in the process? All of a sudden, did purchasing by a cleaner that was cheaper and nobody told you in waste treatment about it, and that cleaner is loaded in new surfactants or new chelants that can really give you trouble in the clarifier process. pH is so critical in that clarifier. How often do you check your probes? I like to calibrate probes once a week minimum, and I always have a pH paper with me, and I'll go up if I'm out walking the line. I'll just go up, get out that paper, and check it, and make sure what the paper is telling me is what the PLC board is indicating the pH is. It's hard for that pH paper to lie. You can get those probes messed up with the coating pretty easily. Mixer speed. You got to make sure that mixer speed. I always like on a clarifier a variable speed mixer. In coagulation, you want a lot of speed. You want a lot of motion. You want to get the coagulant to come in contact with the influent in the system. In the process of flocculation, you want good, medium, steady speed. You don't want to shear the flocculated solid. What I mean by short-circuiting, what happens if you've got a buildup of sludge in that clarifier and you've decreased the capacity? I see that happen a lot. You've got to make sure you've got the proper chemical dose of feed rate. That's just critical and goes without saying. Floating flock. You know, floating flock can give you the same situation that you have with the chelated metals. Your numbers can be high. Yesterday, I was at a plant, and guess what was causing floating flock in our effluent? In this case, it wasn't too much polymer. It wasn't dissolved air in the situation, dissolved air coming from too much oxidant in the system. It was from too much foam. The foam was capturing the flock, carrying it through, and then when it got dissolved in our test in order to run for results on the AA, the numbers were high. When we took when we turned the anafoam on, we took the foam out of the equation and the numbers settled down. Foam will carry flocculated particulate matter through the system and to the city. We don't want that. So if you see any kind of foaming on the top of that clarifier, you got a doggone good shot of that foam carrying the flocculated metals coagulated and flocculated metals out to the city. We've got so many cases out here where the clarifier is too small. And we also have a situation here where anaerobic bacteria will form within a clarifier, especially where zinc phosphating is done on any kind of phosphating. The phosphate is a food source for this bacteria. It will grow, it will metabolize, it will release gas bubbles. The gas bubbles, the microscopic gas bubbles that is, will turn that clarifier into a dissolved air flotation unit, and we don't want to have that happen. Jar testing, you've got to be versed in jar testing. It's great for testing coagulants, polymers, chelating, breaking chelants, determining dose rates. I'll show you what I like to use here. And whenever I'm doing a jar test, I will take my results off my 1,000 ml beaker, apply it to the flow in gallons times the parts per million of the coagulants that I found successful, and I'll divide it by 119,904. 119,904 is my denominator, and that's how many gallons there are in a million pounds of water. And that certainly doesn't lie. For example, if I've got 10,000 gallons of wastewater and I need 2 parts per million of coagulant, I take 10,000 times 2, divide it by 119,904. That tells me how many pounds of that coagulant I need, as you can see here. Now, I know for a fact there's 3,785 mils in a gallon. This is so important for me because when I want to set my pump to give me X amount of mils per minute needed in that system in order to deliver the proper amount of coagulant, I divide my mils, my mils per minute is what I'm looking for here. I like to convert my pounds of coagulant to gallons of coagulant, and then my gallons to mils. And the reason why I like to do this is these coagulants and heavy metal precipitants all have different specific gravities. I want to make sure that I know exactly what my weight is of my coagulant and how much I truly need to add to be where I need to be. So that's very important. I like to make it where I know my mils per minute are going to equal my parts per million needed in the jar when I've done my testing. If those two come together, your chances of success are quite likely. I just want to give you some more ideas of what are complexers and chelants out here. Ammonia is a big-time chelant, and it's prevalent in so many baths out here today. Citric acid, cyanide. Cyanide goes without saying. That's been around forever. And the number one reason why you run a cyanide bath is to keep your metals soluble as long as possible. And the more they are soluble, the wider your operating range is on the plating bath. Your plater is going to want to have the maximum amount of chelant present. Your wastewater treatment is going to want to have the minimum amount of chelants present. EDTA, phosphoric acid, Roselle salts, that's what I use in some of my zinc baths in order to keep it soluble as well. Sodium gluconate, what a great product for a detergent. The problem is it's also a chelant. Sodium pyrophosphate, sodium citrate, tartaric acid, any phosphate, tetrapotassium pyrophosphate is also a chelant. Sodium hexametaphosphate is a chelant. That's what you add when you've got well water and you want to sequester that mineral. Many times you will add sodium tripolyphosphate I've added it in sodium hexametaphosphate. They've all worked well for that. To summarize this, chelators can definitely spoil an operator's happy day. They're complex in type of metals. They're difficult. They can be broken. Your challenge of treating mixed metals is always going to be here if you're going into a job shop metal finishing facility, and each metal precipitates out at different pH ranges. And earlier, if you know, I talked about the fact that trivalent chromium hydroxide and zinc are amphoteric, meaning if the pH gets too high, they're going to go right back out of solution. I want to thank you. I wish we had 3 hours to talk about this, but we don't. But here are some contacts for you as well, should you have questions. And I want to thank you for your time.
Great. Thank you so much, Jim. We do have a question. One of the participants asked, can you briefly describe the standard procedure for metal platers when they need to dump a bath?
When you've got to dump, there's many different reasons why you dump a bath. You don't want to dump the bath completely, but number one reason, if you've got poor filtration, I have so many situations where our filtration process is not keeping up with the quality of the bath. So many job shops out here, especially in the summer, leave the doors open. And you would not believe how much airborne particulate matter can end up in these baths. And what tells them when it's time? When you're not getting throw in the bath, when you're not getting coating thickness, when you're not getting wear resistance, when you're not getting paint adhesion, you've got to go back and look at the bath and find out why. Is the bath dirty? Has it not filtered out? Have you got other contaminants in that bath, such as oxidizers? Have you drugged too much cleaner into that bath through the system? And the number one thing that will cause you to dump a bath is if the racks coming into the bath with the workload on them, if those racks are dirty and if they're not purified, they will drag contaminants into that bath and they'll run one faster than anything. And when you've got to dump that bath, you have a waste treatment nightmare. I've got customers that will bleed and feed those spent baths into the system at a rate that is fast enough to stay ahead of production, yet slow enough to allow for dilution to occur, to allow you to have the rinse waters, if you would, dilute that bath down to make it more tolerable to treat. When they dump the bath, if it's high in metals still and high in the other components, it's going to generate a lot of sludge. If you go to treat a spent bath, you've got to make sure you have the adequate ability to handle the sludge that you're going to generate from the treatment process. I'm building a new bath right now. I'm going to have 4,000 ppm zinc in that bath when I start it. I better not have to dump that or we're not going to handle the sludge. But a dirty bath, excess oxidizer, the inability to properly purify the rack that contains the workload, that can be the major reasons why baths have got to be dumped. In many cases, I like to dummy a bath before I dump it. And what do I mean by that? I will go into the bath with a piece of scrap steel. I'll run my current density, 1 amp per square foot, and I will plate out contaminants onto that steel. I'll take the steel out, and then I'll take the bath and titrate it back to spec accordingly. You really want to make every effort not to dump a bath. I hope that answers the question.
Great, thanks, Jim. We have another question. How do you
Mhm.
remove selenium, strontium, or mercury?
We are working on that right now with a product, and I do not want to use this as a sales pitch at this time, unless you want to contact us later. What we've had to come up with is a dual sulfide slash coagulant proprietary process in order to remove selenium, selenite, and mercury from solution. We have ran into this at power plants. We've ran into this out in mining type situations. And if you have an inquiry about that, you can contact on the webinar. You can contact Kevin Cope and me, and would be very happy to help you with that. We don't want to turn this into a sales pitch, but we have certainly come up with a way to be successful with that, and it requires a proprietary precipitate compound.
Great, thank you, Jim. It looks like those are all the questions that we have, so I want to thank Jim and all of the attendees, and just remind everyone we will send out a PDF copy of the presentation a little bit later today, and also Jim and Kevin Cope's contact information. So thank you again.
Thank you.
Thanks.